Welcome to lecture number 4, Economic Load Sharing among Generating Units. In the previous lecture, we discussed about loss coefficients and we have derived formula for transmission losses and we expressed transmission loss by using a generalized expression, and we discussed about what is the effect of transmission losses on economic dispatch, and we have defined and understood about the penalty factor and what is the need for penalty factor, and we have done one example problem which incorporates penalty factor, by which we understood what is the importance of penalty factor in economic load dispatch. In today's lecture, we will discuss about economic load sharing among generating units. So here we are going to consider two important cases. One is without losses, that means by neglecting transmission losses, by considering PL is equal to 0, the transmission loss power is equal to 0. And second case is we are going to consider the transmission loss. So here the first case is optimal operation without losses. That means the transmission losses has been neglected. So assume that it is known a priori which generators are to run to meet a particular load demand on the station. So just assume that it is already known to us that which generators has to be run to meet our load demand PD. And assume there are k number of generators committed. That means they can start and generate power. And the active power load demand is PD. And the real power generation is PG, where each generator has to be allocated so as to minimize the total cost. The total cost can be expressed as C is equal to summation I is equal to 1 to K Ci into PG of I. So here Ci represents the fuel cost of ith unit. So obviously this Ci is the function in terms of PGI. So Ci is a function in terms of PGI. That means if you want to generate more power output, then obviously you have to spend more money. You have to give more fuel. For example, if it is a thermal power plant, if you want to have more power output, you have to burn more coal, for which you have to spend more money. That means fuel cost will increase. Or if you want to reduce the power output, then you have to burn less coal, then the cost of fuel also will come down. So in both the ways, you can understand that the Ci is the function in terms of power outputs of each and every unit. And this total cost can be expressed as sum of individual cost of all the units. And this cost can be expressed in terms of rupees per hour. And this total cost should be minimum provided the inequality constant are satisfied. So one of the important inequality constant here is the active power output of each and every unit. So this active power output or real power output of each and every generator should be within their minimum and maximum limits. Suppose if the total power generation of any unit is less than minimum limit, then there is no meaning of using that generator and spending some money in generating power. At the same time, you cannot operate the generator beyond its maximum power capacity, because that will lead to overloading of generator, so which will increase the temperature rise, and then ultimately it leads to failure of the generator or damage of the generator. So always here the power generation of all the units, if you take the sum, that should be equal to power demand. So you can say the total power generation should be equal to the total power demand. And of course here we have neglected the transmission losses. So for this case, you also need to take care of spinning reserve. It's not that very much ideally, the exact power total generation should be equal to power demand. We should also have some excess power generation, because whenever the load demand rises quickly, at the same time you have to raise the power generation also. So for that you should have some spinning reserve facility also. So since this cost function is a non-linear function and Ci is independent of Pj, where j is not equal to I, this is a separable non-linear programming problem. So that means the fuel cost of one plant or one unit is not dependent on the fuel cost of another unit. So where everyone is a non-separable entities. Assume that any quality constant is not effective, then you can express the same equation as summation PGI is equal to PD, or you can bring this PD to LHS side, then it will become minus PD is equal to 0. So this problem can be solved by method of Lagrange multiplier, which is used for either minimizing or maximizing any function with the side conditions in the form of equality constants. So basically ours is a optimization problem, so that can be solved by using this Lagrange multiplier method. So now let's try to incorporate this method for our problem. So once you want to express by using this Lagrange multiplier method, the augmented cost function, or that can also be called as Lagrangian, can be expressed as C bar is equal to C minus lambda into summation I is equal to 1 to K PGI minus PD, where lambda is the Lagrangian multiplier. So now we have to minimize this total cost. That's what our problem. Our objective is to minimize this total cost of generation. So for that, differentiate this cost equation with respect to its variable. The variable here is power output of each and every generator, that is PGI, and equal to 0. So dou C bar by dou PGI is equal to 0. This is the condition by which you can minimize the total cost of generation. Or you can also express this same equation as dCi by dPgi is equal to lambda, where I is equal to 1, 2, and so up to k, where k is nothing but k number of units are there. K represent that there are k number of units. And this dCi by dPgi is called incremental fuel cost of ith generator. And it can be expressed as, let me write here separately so that you can understand, dCi by dPgi. So numerator is the cost. So this numerator cost can be expressed as rupees per hour, whereas this denominator is PGI, that is power output of ith generator. So the power output is usually of very much high, so that's why I'm expressing as in terms of megawatt. So combinedly, the unit of this incremental fuel cost is given as rupees per, here hour into megawatt, so it becomes rupees per megawatt hour. So that's what here it is expressed. So this particular condition can be expanded for each and every unit. Then it can be written as dC1 by dPg1 is equal to dC2 by dPg2 and so on up to dCk by dPgk, that is equal to lambda. So now this is the condition for economic load dispatch when you neglect the transmission losses. The same condition can be expressed in terms of what's as the optimum loading of generators corresponds to the equal incremental cost point of all the generator units. That means if you want to allocate the load among k number of units optimally, the condition is stated as the incremental fuel cost of all the units should be same, and that should be equal to Lagrange multiplier lambda. And this particular condition or equation is called as coordination equation. This particular condition or equation is called as coordination equation, that is mentioned over here. So the summary is, whenever you neglect the transmission losses, the condition for economic load dispatch is the incremental fuel cost of all the units should be same, and that should be equal to lambda. Now coming to the second case, in the earlier case we have neglected the transmission losses, but now here we have to consider the transmission losses. So when we consider the transmission losses, there will be a change in the power balance equation. Just in a similar way to the previous case, we are going to derive the condition for optimal operation with losses now. The equation 1.48 represents the total cost of generation, where each and every cost of generation of each individual unit is the function in terms of its power output. So at any time under equality constant of meeting the load demand with transmission losses, you can express the equation as summation I is equal to 1 to m PGI minus summation I is equal to 1 to n PDI minus PL is equal to 0. So where PGI is nothing but power generation output of ith unit, and PDI is the power demand at ith unit or ith bus, and PL is nothing but power transmission losses. In a simple words, you can understand this as the total power generation PG should be equal to the total power demand plus the total power transmission losses. So this particular equation, as I mentioned many times in the previous lectures, it is called as power balance equation. This particular equation is called as power balance equation. So from this you can express summation I is equal to 1 to m. You can take summation common here. So then it becomes PGI minus PD minus PL is equal to 0, where m represents total number of generating plants and n represents total number of buses and PGI represent generation at ith bus. So now let's try to incorporate Lagrange multiplier method for this case also, just similar to the previous case. So the PD can be expressed as sum of all the load demands connected at all the buses. PL is the total system transmission losses. So now Lagrange cost function or Lagrangian can be expressed as C bar is equal to summation I is equal to 1 to m Ci of PGI minus lambda into, now here we are trying to incorporate power balance equation. And again this total cost of generation can be expressed in rupees per hour. So this particular equation follows that for a given real power demand PDI at all buses, the system loss PL is a function of active power generation at each and every plant. And in the subsection also it can be shown that if the power factor of load at each bus is assumed to remain constant, the system loss PL can be shown to be a function of active power generation at each plant. So that means you can express this statement mathematically as PL, the total power transmission loss, is also a function of transmission loss of individual power. So for the optimal real power dispatch, we have to differentiate that total cost equation with respect to PGA and equate to 0. So then if you modify this particular equation, we are going to express this equation 1.52. dci by dpgi whole divided by 1 minus dou pl by dou pgi, that is equal to lambda, where this particular dci by dpgi is nothing but IC. IC is nothing but incremental fuel cost. incremental fuel cost of ith unit into Li. So where Li is nothing but penalty factor, so which we have discussed in the previous lecture, lecture number 4. So this penalty factor can be expressed as 1 by 1 minus dou PL by dou PGI. So here the partial derivative dou PL by dou PGI is called as incremental transmission loss. In short, you can call it as ITL. So based on that, you can express this penalty factor as 1 by 1 minus ITL. If you want to express in general, then indicate suffix I. So where I can be taken as 1, 2 or so and so on up to M. So now this particular condition or equation 1.52 is called as exact coordination equation. This particular equation is called as exact coordination equation. The reason why it is called as exact is here we have not neglected the transmission losses. Whatever the powers are there in the real power system, starting from generation, transmission loss and distribution power. So all the powers we are incorporating. So that is the reason here it is called as exact coordination equation. So in terms of words, we can say this particular condition as whenever we consider the losses, the condition for optimum allocation of loads is the product of incremental fuel cost with its penalty factor should be same and should be equal to lambda. Or in general, this particular equation can be expanded as dc1 by dp1 into L1 is equal to dc2 by dp2 into L2 and so on up to equal to lambda. So here this each and every term represents the product of its penalty factor and incremental fuel cost. So in terms of words, the statement or the condition can be stated as the product of incremental fuel cost and penalty factor of each and every unit should be equal, and that should be equal to lambda. So that will give you the condition for optimum allocation of load among various n number of units when you consider the transmission losses. So now let's try to solve one numerical problem based on these two conditions. So the problem is given as the incremental cost of two generating units are as follows. IC1 is the incremental fuel cost of unit 1, that is expressed as 0.1 into P1 plus 25 rupees per megawatt hour, and IC2 is the incremental fuel cost of unit 2, that is equal to 0.2 P2 plus 18 rupees per megawatt hour. Given that the minimum and maximum powers are 10 megawatt and 100 megawatt for each unit, we have to allocate a total load of 100 megawatt optimally across these two units. So now let me try to give the picture of problem so that you can apply the given conditions and solve it. So here the incremental fuel cost of two units are given and the minimum and the maximum power limits are given for both the units. That means the power outputs of two units P1, P2 should satisfy this condition. P1 and P2 should be within the range of 10 megawatt and 100 megawatt, where this 10 is minimum power output and this 100 is maximum power output. And here it is given as incremental fuel cost IC1 and IC2. So this IC1 can be expressed as DC1 by DP1. This IC2 incremental fuel cost of plant 2 can be expressed as DC2 by DP2. Just now we saw that the condition for economic load dispatch is two cases. One is without losses, another one is with losses. So in the given problem, there is no information with respect to losses. That means you can consider this particular problem under case 1. Under case 1 means optimum allocation of load without losses. So the condition for optimum allocation without considering losses is the incremental fuel cost of 2 units should be same. That means dC1 by dP1 should be equal to dC2 by dP2. That should be equal to lambda. And here there is a total load of 100 megawatt. So maybe you can take this as equation 1. And based on this given statement, you can write the total load should be supplied by using these two generators itself. That means you can take the sum of two power outputs P1 plus P2 should be equal to the total load demand 100 megawatt. So this was the given by the total power generation should be equal to total power demand. This is by using power balance equation. So here total power generation can be expressed as P1 plus P2 as there are two number of units. So take this as equation 2. So by solving these two equations 1 and 2, you can solve for the values P1 and P2. So that will complete the solution of the given problem. So let me show the solution here for your reference. Here the solution is given. You can see. So based on the equation 1, you can equate these two, IC1 and IC2. That is nothing but 0.1 P1 plus 25 is equal to 0.2 P2 plus 18. You can simplify this further, then it will lead to this. And the given load is 100 megawatt, as I told, that need to be supplied by using these two units itself, P1 plus P2, that should be equal to 100 megawatt. So now let's say this is equation 1 and this is equation 2. So solve these two equations, then you will get P1 value as 43.3 megawatt and P2 as 56.66 megawatt. Now you can check, cross-check whether these two generators are operating within the limits or not. So P1 value is 43.33. So it is falling within this range because 43.33 is within the range of 10 and 100. And similarly, P2 value also is falling within the range. P2 value is 56.66 megawatt. That is also falling within the range, 10 megawatt and 100 megawatt. So here you can conclude that these are the final scheduled powers for two power plants. Suppose let's say if you got P2 value is equal to something like 110 megawatt. So which is nothing but violation of this limit. So during that case, we have to fix P2 value as 100 megawatt because the maximum capacity of P2 is, the plant 2 is 100. So you have to fix that to 100 because the actual power generation 110 is very close to this maximum limit. Then you can determine the value of P1. So obviously P1 will become 10 megawatt. So that you can substitute 100 plus 10 will become 110 megawatt. The 0 megawatt. Then there is no need of using that power. Or let me take some other value for your understanding. Let's say, for example, if P1 value is given as or determined as, let's say if P1 is determined as some 5 megawatt of power. So which is nothing but the violation of this condition. It is nothing but violation of this condition because 5 megawatt is lower than the lowest limit of limit. Then you have to fix this P1 value as 10 megawatt. Then the remaining value of power P2 will become 90 megawatt. The 90 plus 100, you can fulfill the entire load demand. So this is another case where once you determine the values of P1 and P2, if those values are not falling within the range, you have to adjust those values. Of course, that adjustment is not economical operation. So now, let me explain what are the various ways the same problem can be modified. What are the possible modifications can be done in the same problem so that most of the times the students will get confused. Actually speaking, once you understand the fundamental conditions and the procedure of solving the problem, even if the problem is modified into multiple ways, you can solve it. See, in the problem, the incremental fuel cost equations are given. So instead of giving incremental fuel cost, the one probable case is, instead of giving incremental fuel cost, the cost equations may be given. C1 and C2 may be given. Then you have to get IC1 and IC2 by using the given cost equations C1 and C2. So that might be the one probable modification you can have. And the second thing is, here the minimum and maximum power limits are given. Suppose in another case, there may not be any limits. So the limits may not be given sometimes. If that is the case, you no need to worry about the P1 and P2 values. Whatever the values you get for P1 and P2, that itself will be the final values. That is another case. And here the total load demand 100 megawatt is given. Sometimes the problem can be given like you have to find the cost C1 and C2. So once you get the optimum values of P1 and P2, if you substitute those P1 and P2 values in the equations of fuel cost, then obviously you can find the C1 value and C2 values. And sometimes the question can be modified like you have to find the total cost of generation, total fuel cost of generation. Then that can be determined by using total fuel cost is equal to C1 plus C2. So first you have to find individual fuel cost by using the respective power values P1 and P2. Then if you take the sum, that will give you total cost of generation. And the one more possible case, little complex case is, sometimes the question can be framed like, suppose if the load demand is divided equally. So that means equal load sharing. Let's say in the previous problem, we got P1 and P2 values as 43.33 megawatt. And P2 we got something around 56.66 megawatt. These are the answers we got in the previous case for the same problem. Now I'm trying to explain how the same problem can be made little more complex by incorporating this case. The case is like, these are the values we got when the load demand is 100 megawatt. And this is the optimal allocation. Suppose instead of going for optimal allocation, if we allocate the total load demand 100 equally across 2 units, that means both P1 and P2 should be equal to 100 megawatt. Then what is the loss or profit with respect to cost? That is the question may be asked many times. Then how we have to solve that problem? So first for the case 1, for the values of optimum, you have to find the total cost generation. And then by using these equal load values, that means by considering P1 and P2 equal to 50 megawatt, you consider or calculate C1 and C2. Maybe you can take this as C1 dash and C2 dash. Then you can determine the total cost of generation. CT dash is equal to C1 dash plus C2 dash. So once you have CT value, where CT corresponds to total cost of generation for optimum allocation. where CT dash is the total cost of generation for equal load sharing. Both values will not be same. So now whatever you want to observe, whether it is a saving or loss, that can be determined by comparing CT and CT dash. So once you differentiate take the difference of these two cost values, then you come to know whether it is a loss or profit. So that is how in multiple ways the same problem can be modified. So in today's lecture, we have seen the conditions for optimum operation or optimum economic load dispatch without losses. So that is nothing but DC1 by DP1 is equal to DC2 by DP2, that is equal to lambda, where this particular equation is called as coordination equation. We have seen this case 1. And next we discussed about the case 2, that is optimal operation with losses. So with losses, the condition will be modified as DC1 by DP1 into L1, that is equal to DC2 by DP2 into L2, that is equal to lambda Lagrange multiplier. So this particular equation is called as exact coordination equation. So we have seen the derivation of these two conditions, and we made an attempt to understand these two conditions, and then we have used these two conditions and solved one numerical problem. And then we have seen in how many ways the given problem can be modified to create some sort of confusion, but very easily you can solve any problem once you remember these two given conditions. So that's it for this lecture. Thank you all. We'll meet in next lecture.